Good afternoon. My name is Melanie Wooden, and I'm the Dean of the Faculty of Arts and Science. Before I begin, I wish to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. I'd like to welcome you all to the Martin Lecture Series. The Faculty of Arts and Science created this series to honor the Martin family for their long association with our faculty and university, including through an extraordinary legacy gift. The Mary Louise and Ronald Laidlaw Martin Graduate Scholarships will enable the Faculty of Arts and Science to attract brilliant students from across Canada and around the world. The Martin Graduate Scholarship in Physics is awarded to top students working in experimental high-energy physics. Home to 6 Canada Research Chairs, U of T's Physics Department and its core focus areas such as quantum optics, particle and biological physics, has helped the university earn the top ranking in Canada for physical sciences and among the very best public universities in the world. This legacy gift from the Martins represents all the great qualities we see in our donors, a passion for learning, and a desire to invest in the next generation of scholars. We are grateful for their generosity. As you're aware, this has been a year like no other, and the fact that this year's lecture is a virtual event is a sign of these times. But even though we can't be together, this lecture will give us a unique opportunity to hear about one of the hottest topics in physics right now and what it holds for the near future, quantum computing. And to help us explore this and other fascinating and somewhat mind-bending aspects of quantum computing, we're honored to have with us today's keynote speaker, one of the world's foremost experts and scholars in his field. Professor Christopher Monroe is a leading atomic physicist, quantum information scientist, and quantum computing engineer at the University of Maryland. Following the lecture, a Q&A session will be moderated by Professor Kimberly Strong, Chair of the Department of Physics at the University of Toronto. So please type your questions for Professor Monroe into the Q&A feature at the bottom of your screen, and Kim will get to as many as possible. So please join me now in welcoming this year's Martin Lecture speaker, a trailblazer in the field of quantum computing, Professor Christopher Monroe.
Okay, thank you, Dean Wooden, for that kind introduction. And I'd also like to thank, of course, the Martin family for so kindly supporting this lectureship, and I'm delighted to be, I understand, the second runaround in the lecture series. And I understand all 4 Martin siblings are in attendance. Some of them are even physicists, so I'm going to have to be careful. And please please ask some questions if things are troublesome. So I'm going to share screens here, and we'll get started. I would love to be there in person. Toronto is one of my favorite cities, and I'll have to take a rain check. I have a lot of friends there, so I'll visit soon. Okay, I assume everybody can see this. So I will indeed be talking about the topic of quantum computing, which is a radical, revolutionary new form of computing. And I want to be very high level in my discussion, define what it is, why it's different. And it's fitting for this lecture because this is not just a physics audience. The Martin lectures are much broader than just physics. And quantum physics is much broader than physics too. It borders on philosophy. There's lots of weird stuff in there. And that's, in a sense, what makes it difficult to grasp. Although I'll talk a little more about that. I don't think it's hard. It's very easy to teach. It's just that the rules are a little confounding, and I'll talk about that in a bit. So this picture here is of individual atoms. Those white glowing dots are each single atoms. They're charged atoms, so they repel each other, and that's why they form this crystal. And we're pushing them together with extra forces. This turns out to be one of the most clean media for doing quantum mechanics. And the reason is these atoms are all the same. They're incredibly well isolated from the environment. And you can see them because we're shining laser light on them. When we want to interrogate these quantum systems, we can do it from the outside world with great control. As Dean Wooden said, I'm from the University of Maryland, just on my way moving down to Duke University, although I'll retain appointments at both places. And we're starting a new quantum center down at Duke. I'll also, toward the end of the talk, go industrial on you and tell you a little bit about the company IonQ, which is a quantum computing startup just inside the Washington, D.C. Beltway in College Park, Maryland. Okay, so let's. This is the funnest part, introducing the topic. It's so fun to talk about this because quantum computing, to me, I've been studying quantum physics for a long time, but I didn't know much about information theory, the theory of information. And you could argue that quantum physics and information theory were really the two greatest scientific advents of the 20th century. There are many, of course, that are, but these are very fundamental, theories of both nature and how we perceive information. And quantum computing mixes the two. So, like I say, it's been a journey for me over the last 25 years to learn information theory, learn about the theory of computing, because this is a totally different way of computing, and I want to really try to motivate that for you. So in turn, I want to talk briefly about information theory, and I will only talk very briefly, partly because I don't know it very well. But you probably know that information is carried in characters, alphabet, letters, or at the most fundamental level, bits, zeros and ones. And we, of course, can even store the Bible in zeros and ones. Any information can be represented by zeros and ones, a string of them. Now, these two gentlemen, Alan Turing and Claude Shannon, I would say in the mid 20th century, they invented the concept of information theory. And while they prefaced the first digital computers in the mid 20th century, I wouldn't say they invented the computer, but they invented a formalism, a mathematics that allowed people, engineers and such, to find devices that could represent bits and compute. So Turing, for his part, you may have heard the term Turing machine. A Turing machine is a so-called universal computer. Any computer can be mathematically modeled as a Turing machine. And all you need is a tape that has zeros and ones. This could be real tape with holes, or it could be little magnets that can be flipped. And it requires a memory with some zeros and ones, some bits also. And the tape moves across this head. And if you can do some kind of conditional flip of bits, depending on what's in the memory, you can program it to do any computation at all. It's very abstract, and nobody's really built a machine that actually looks like this, but it's a mathematical model of computing. Shannon, for his part, is largely owed with the definition of the bit itself, the binary digit bit, 0 and 1, and he quantified information. How random a bit stream is of zeros and ones tells you how much information is in there. And both of these advents really pushed the field along, because people started thinking, well, what can be a 0 and 1? A switch can be a 0 and 1. So there were vacuum tubes that were the leading electronic switches at the time, and vacuum tubes became the basis for the first real computers, the first digital computers, in the United Kingdom in the mid 40s, the US slightly after that, and actually the USSR slightly after that. And so these monstrous machines had thousands of these vacuum tubes that were not very reliable. They would break a lot. So there were even full-time engineers who were tasked with replacing broken vacuum tubes. That's what they did. I love these old pictures. Here's another old picture, a very famous one, also from the 40s. This is the first solid state switch, the solid state transistor. And what's remarkable is that this is basically the same physics that goes on in your iPhone. Of course, the iPhone has transistors that are really tiny. This thing doesn't look very stable. It doesn't look like it's very reliable. In fact, it wasn't. What you see here is this triangle thing it's just a piece of glass. It has a gold film on the bottom. This dark crystal on the bottom is it's called a semiconductor, and it's germanium. When you apply a current through this gold leaf here, it will direct a larger current to flow. You can't see you can't see the third terminal here at the forefront of the picture, but by turning on this current, you can switch that current on or off. It's a switch, but it's all electronic, and importantly, it's all solid state. It wasn't a vacuum. So these things in principle could be very stable. And in fact, over the many decades since 1947, engineers and scientists developed better and better semiconductor materials, in particular silicon, which turned out to be manufacturable in a way that germanium wasn't. And lo and behold, we have something called Moore's Law, which I'm sure you've probably heard of as well. Well, this is a depiction of Moore's Law, which basically has these transistors getting smaller and smaller every year. So this plot here is the number of transistors on a single chip versus the year, just over the last 30 years, 30 or 40 years. And this is a logarithmic plot. That means every division here is a factor of 10 increase. And when you have growth that's linear on a log plot, that means exponential growth, sort of like compound interest, only here the transistors are getting twice as small every couple of years. And so this is why Moore's Law was able to capture the information era and make computers economical. And the number of transistors on current processors is now in the billions, approaching trillions. It's really remarkable. And it has to do, it's not exactly, this picture doesn't give it justice, but the fact that silicon can be manufactured to scale and made very small and reliable is really what's going on here. Okay, so there's the brief treatise on information theory. And notice we always end with some device or some way with which you can store information and do something. Okay, now to quantum. Well, around the same time as the silicon era was building up steam, a colorful physicist by the name of Richard Feynman presented this wonderful lecture at Caltech in 1959. And he was talking about, he was a theorist in quantum physics, but he was a tinkerer. He loved what was going on in the mechanical world. And he saw in these solid state transistors that you could really shrink them down. He saw many decades before the possibility of shrinking transistors down to really small levels. And so in this lecture, there's an amazing paragraph here. And he says, well, what happens when you shrink the circuit down to just a few atoms? It gets really, really small. They weren't even close to that in 1959. But he was wondering what would happen when you do that. And being the great physicist he was, he could smell something interesting there. And the reason is, when you get to the very, very small and very, very simple, the laws of physics actually change. That's probably, some physicists wouldn't like the way I said that, but the laws of physics are clearly different when you're at the very small and very simple. These laws are called quantum physics. And Feynman realized that, well, when you change the laws of physics, there have to be new opportunities for design. Okay, so let's talk about that now. I said earlier that quantum physics is easy. It actually is. The rules are really easy, and I'm going to tell you the two and only two rules of quantum physics in hopefully under 5 or 8 minutes. They're not that hard. Okay, you may have heard that quantum physics, quantum mechanics is a wave theory. It describes everything as being a wave. Well, yes, that's true. But there's something very funny about that wave. And let me get onto it. So I like when I teach quantum physics, I teach it from this perspective. I teach it from the perspective of exactly two rules. I'll call them golden rules of quantum mechanics. Sorry for this loud yellow. I want to grab your attention here though. Okay, so quantum things are waves. And one property of any wave, sound wave, a light wave, a pressure wave. A wave is not localized, and it's not necessarily in one position. It can be the place. We say in math, hello, my computer just died. I don't know if you can hear me. Can anybody hear me? Sorry, my computer just froze on me. Oh, okay. I'm getting a message that I can be heard. All right, well, let me get back into it. I think we're okay. All right. So sorry about that. Okay, where was I? I was talking about rule number one. So the feature of waves is that we say they can be in superposition, right? If you think of a sound wave, if you play two notes on a piano, your ear can vibrate in two frequencies at the same time. You can hear them both. This is an indirect property of waves. But if you throw a rock in a pond, we know that the wave that emanates, sorry. I think somehow the screen wasn't sharing. Okay, I think we're good now. So sorry. So when you throw a rock in a pond, we know very clearly what happens. I'm going to read the chat here to make sure everything's good. We're back in business. Yes, sorry. Okay, so finally, when you throw a rock in a pond, we get this circular wave that emanates from the source, and that wave is everywhere. So it's not like a particle. It can oscillate and be in many places at the same time. We call that superposition. And so if something is described as a quantum object, that is, it's very well isolated, and it's a simple system. Usually these are very small atoms or electrons. They can be waves and they can be in superposition. And in fact, there's a wave equation that describes how this superposition moves around. And the math, it can get a little bit complicated. We can even represent a wave. This is a very funny way to draw an atom. You've probably seen these drawings. It's called a Bohr atom, where we think of this is one electron here in blue. It's in two orbits at the same time. Why? Because it's a wave and it's sort of fuzzy. It's in both orbits. We can label the two orbits as 0 and 1. And at the most basic level of quantum mechanics, we have something called a qubit, a bit that can be both in 0 and 1. And what's important is that the weighting of how much 0 and how much 1 there is given by numbers that carry information. And by the way, a little notation here, don't get too upset here, but this line and funny greater than sign, this arrow, what that means is that's a quantum state. We're describing this as a quantum state, like the electron being in this orbit versus the other orbit, okay? It's just notation. It's not hard. It's just memorization. What's interesting is these A and B numbers, they follow a wave equation. It's called the Schrodinger wave equation, but it's just like the wave equation for water waves or sound waves going through air or light waves going through space. It's a wave equation, and it's a different, it's a second order partial differential equation. Yeah, whatever. That's how most folks teach quantum mechanics. They hide under the mathematics, and the mathematics can get hard. Well, the mathematics for water waves can also get hard. In fact, the mathematics for water waves is nonlinear. I would say it's even harder than the wave equation in quantum. So we shouldn't be afraid of quantum mechanics just because of the wave equation. The reason we need to be afraid of quantum mechanics, or the reason it's strange, is that what's going on here? We have one electron and it's in two places. You know, if I have a can here, a can of soda, it can be in two places at the same time, according to quantum mechanics, if the can is described as a quantum system. And that's the rub. That's why we need two rules and not one rule. Okay, rule number one, I tried to, okay, there's a lot of mathematical complexity if you want, but there's not much conceptual complexity in rule number one. We have a wave equation, and A and B can change and so forth. They can oscillate. So what's strange is that rule number two has to be used to reconcile with reality. And a little bit tongue in cheek, I say rule number two says that with that superposition thing, that you can have things in two places, that only works as long as you're not looking. All done, very neat. Kind of ridiculous in a way. Very high level physics laws aren't typically like this, but we have to have this. And this is the disconnect between the physics of the macroscopic world we live in and quantum physics, because this can, I mean, we're looking at it. Even the air in the room knows where the can is, right? If the can is in two places, the air in the room has to know where to evacuate. So rule number two, we need this to ensure sanity, I guess, in the everyday world. And what's a little more interesting about rule number two is that it also tells you how to calculate what happens when you do look. Well, if we have a superposition of 0 and 1 and we observe it, we look at it, it will randomly pop into one or the other, but it will be a definite state, whatever that state is. It's going to be definite, but we can't tell what it's going to be beforehand. So two things that are very strange, and this is where philosophy can start. Well, rule number two, it seems that by merely looking at something, you affect that something. And that's very strange. There's no physics that has that we know of up to quantum physics. By looking at something, you should be able to passively observe something without changing it. But quantum mechanics says there's a necessary link between observation and action. The other thing that's weird is that the probability of getting the state 0 or 1 when we have a superposition is given by A and B. Forget it, that it's A squared and B squared, that's just technical, but it's given by the weights of the superposition. So if we have a 90-10 superposition, 90% of the time we're going to get 0, 10% we get 1. So if, we all know and use probabilities all the time, but in everything but quantum physics, probabilities are used to characterize our ignorance. Like when you toss a coin, we don't know how hard we toss it, or the weather. It's such a complicated system in the upper atmosphere. There's so much stuff going on. So we're ignorant. So we have models that calculate probabilities. But in quantum physics, these probabilities are absolutely necessary. It's not about ignorance. It's there. It has to be there. And that's very strange. Probabilities, actually, when you think about it, are kind of strange because it means there's something cooking the books. Something is behind, there's the casino that's changing the odds on the dice. But in quantum physics, the randomness comes right at the fundamental level of the theory. And this is why Albert Einstein rejected quantum physics largely. You know many of his quotes: God does not play dice. He also said, well, when I turn my back on the moon, is it still there? Because I'm not looking at it. So he was being a little bit silly, but his heart was in the right place. These are very strange rules. And I'll say one last thing about these two rules. In physics, we like to think of physics, we're elitists. We like to think of physics as the king of science, the most fundamental. Well, the most fundamental science has one law at the very top, and then everything is derived from it, like F equals ma. Newtonian mechanics is all derived from that. Well, here we have two rules, and you can't not derive one from the other. We have two separate pyramids, and they seem to be totally unrelated. Okay, so this is, it's weird. It's not hard, it's just strange. Once you learn the rules, it's actually very easy. Okay, so there's only one, there's probably a few more, but there's one really good analogy to these, to quantum superpositions. And this will involve an optical illusion. So you've probably done this when you draw a cube on a blackboard with ambiguous perspective. the question is, oh, by the way, this in art, they teach you to make sure these lines are converging to a point in the distance. Well, these lines are absolutely parallel, so it's ambiguous. This is not the way to draw perspective. It's an ambiguous perspective. So my question is, what's the front face? Is it pointing down and to the left, or is it pointing up and to the right? Well, that's a little bit like a superposition. It's sort of both. What's great about this analogy is that rule number 2 is present here as well, because when you lock onto a perspective, you tend to stay there. When you lock onto bottom, this face pointing bottom to the left, it tends to stay that way. So this is a lot like a quantum bit. Let's see, was there any audio issues? I saw something in the chat there. I'll pipe in if there is. Okay, so this is a little bit like a superposition, but of course there's nothing quantum about this. It's an optical illusion. But the great thing about this is that it works for multiple bits. When you put 2 of them together, you see something even more interesting. We find that the perspective of the 2 cubes is typically the same when you measure it, when you lock onto one perspective. They're generally the same, although they should be random. So there's this correlation between these 2 cubes. And if you close your eyes and shake your head, you can maybe see the other 2. So this feature in quantum mechanics is called quantum entanglement. You may have heard that term. It has to do with the fact that superpositions of more than one qubit, more than one quantum bit, can be they can be a superposition of 0, 0, and 1, 1. And if you have a superposition of 0, 0, and 1, 1, you always see those 2 bits are the same. They're both 0 or they're both 1. But individually, the bits are totally random. You see what I'm saying? So they're perfectly correlated, but individually random. And while this optical illusion goes away when the cubes go far apart, in quantum mechanics, this entanglement can persist over very large distances. And that means that there's sort of a connection without any real connection in a way. I mean, I should put quotes around that, but here's another Einstein quote: spooky action at a distance, entanglement. He thought that entanglement meant that quantum was really wrong. There's something wrong here because we can't have this funny action at a distance without any physical force. Okay, so with this, there's a little bit of, we have a little bit of background now to dive into quantum computing. What is a quantum computer? Finally. Well, a quantum computer computes with qubits instead of regular bits. And in general, it computes with entangled superpositions of qubits. And so let me tell you sort of how that works. And this is a very high level definition of a quantum computer. And I like to describe it in terms of good news, bad news, and then finally, very good news at the end. Okay, so the first piece of good news is that when you put quantum bits together, there are exponentially many possibilities. All right, with 3 qubits, there are 8 3-bit numbers, 0, 0, 0, all the way to 1, 1, 1. And here I've written the most general quantum state of 3 bits. And I have 8 weightings here, A0 through A7. Now that's not very big. 8's not very big. But if this were 300 qubits instead of 3 qubits, I couldn't. There's not enough space in the universe to even write it down because I would need 2 to the power 300 different variables. And there's only 2 to the power, I think, 250 atoms in the entire universe. So this is the exponential growth. And this, I would say, is the big opportunity that Feynman saw in 1959. The big opportunity is that with entangled superpositions, you get exponential growth. So in this case, we're computing a function. It doesn't matter what the function is, but we can sort of compute the function in parallel. So you can think of this as massively parallel processing. Exponentially massive parallel processing, which is really, this is amazing news. We can continue on Moore's law without worrying about shrinking things because we get extra boosts from quantum. Okay, well, what about rule number 2? Well, this is going to be the bad news, right? If we compute 2 to the 300 outputs, we can't look at them. They're sort of useless. And when we do look at them, we only see one output. We only see one answer. These gray levels are supposed to be like the weightings here. They all add to one. And when we measure when we measure only one of them, when we measure the output here, we only get one answer. We only get one n bit number. And we have no idea what it was because it came with probabilities, and it's a mess. The bigger the system, the worse off this is. So this is not very useful. And in fact, I'm sure Feynman recognized this right away. He didn't really see the path to quantum computing. That took another 30 years or so. And this fellow here, David Deutsch, is largely attributed to having put it together. The idea here at a high level is fairly simple. You have all these exponential inputs. You can't write this down. I mean, there's so many, there are so many possibilities. Now, they interfere just like any wave interferes. These are quantum waves, and they interfere. They can interfere constructively, like two water waves can reinforce each other, or they can cancel each other out. But in this case, these red dots are sometimes called quantum gates, just like gates in regular computing. And if we can cook up an algorithm that amounts to lots of interference, so that only one, this arrow is supposed to point to the white dot here. The algorithm produces one output state or a few output states, and then when we measure it, there's no randomness anymore. And so that's the magic of quantum computing. It allows you to calculate something that depends on all these inputs, but you don't have to worry about measuring with all this randomness. The algorithm takes care of it for you. Again, the arrow is supposed to point to this one, and this output here can deterministically depend on all the inputs. What that means is that it can compute something interesting with an amount of memory that you could never do on any classical computer, any regular computer. Okay. So one of the biggest applications, and this really put the field on the map about 25 years ago, is the algorithm Peter Shor developed to factor numbers. So we can factor small numbers easily. 15 is 5 times 3, 39 is 3 times 13. But if I give you a really large number, it's actually very hard to solve the two numbers that multiply together to give that original number. And in fact, it's such a hard problem that the basis of almost all modern encryption is on the inability of factoring big numbers. So the so-called RSA algorithm for encryption, we all use it every day with their credit cards. It's based on having very large numbers that nobody can factor. Well, a quantum computer can factor numbers fast, exponentially faster than any classical computer. That's what Peter Shor showed. Very loosely speaking, here's how it works. So if we want to factor the number 39, we get a bunch of quantum bits. I guess we need at least 6 quantum bits, because 2 to the power 6 is 64. So we store, I'm reading these in decimal here, we store a superposition of all these numbers, and then we run the algorithm, and it turns out the algorithm will change the wave function here, that is the superposition of all these inputs, to this. Magic. It turns it into a superposition of 3 and 13. And then when you measure the output, you'll get one of these two numbers, and you'll be able to factor the input. That's basically how it works. There's a lot of details in there, but the important point is to go from here to here is not exponentially hard in the size of the input. So it's an easier way. Now, it turns out to factor an interesting number means we have something like 2,000 bits, or so that's a 500-digit number, and we're going to need lots of qubits to do this. It's a big problem. You need billions, if not trillions, of operations. It's one of the hardest applications we know of, but it's also one of the cleanest ones, because there's a proof that it's better than anything we can do that we know classically. So this is a research field. There's lots of thoughts on other problems out there, and we're looking for problems where one answer depends on lots of inputs. And so an example is optimization, where if I ask you, okay, in this mountainscape, where's the tallest peak? Well, you can simply look at it and say, well, there it is. It's right here. And that's because a landscape only has 2 dimensions. It has a latitude and a longitude, and you can sort of look at it. But if I give you a function with 1,000 variables, like maybe a financial model where those 1,000 variables are like, I don't know, the interest rate in Japan, the inflation rate in Venezuela, and so forth, and 1,000 other variables. What I would like is what minimizes this nonlinear function of all these variables. Those turn out to be really hard problems, and there's lots of them. Optimization, it seems there's no strong proof like factoring, but it seems like optimization is very interesting for quantum computing. And by the way, if we want to understand a complex molecule, the electrons that bind on a very complex molecule do their own optimization. The electrons, they repel each other, but they have complex interactions. And just with 100 electrons or so, we can't even calculate the binding energy of a big molecule. A quantum computer might be able to do this, and there's lots of ideas on how to do that. Logistics problems like the traveling salesman problem, there are no proofs, and in fact, it's largely thought that a quantum computer can't solve the traveling salesman problem, but it could produce an approximation that's better than anything classical. Again, this is very researchy, finding the algorithm, the killer app for quantum computing. That's one of the big goals in the field. Okay, I want to now spend the rest of my time in the lab. So after introducing quantum computing, you might ask, well, what does it take to build one of these things? Why is it so weird? I mean, everything's quantum. Why can't we just assemble atoms and make a quantum computer? Well, okay, the problem is those rules, rule number 1 and rule number 2. Remember, rule number two says that the superposition where all the action happens, all the entanglements, it only happens as long as you're not looking. So you need nearly perfect isolation, and that's pretty exotic. So I like to quote my colleague Bill Phillips at Maryland and NIST, a Nobel Prize winner in atomic physics from the 90s. He says sometimes that a quantum computer differs more from a classical computer, from a laptop, than the laptop differs from an abacus. And what he means is that this laptop and the abacus are really both Turing machines. One has super fast transistors with maybe 1 billion of them on a chip. All right, the abacus is pretty slow, but they compute using the same fundamental laws. Whereas the quantum computer has totally different laws than a laptop. And so I think a corollary to this quote is that why should we think that a quantum computer will look anything like this laptop? Why would it be built out of silicon? Because it's very hard to isolate individual atoms of silicon that are part of a solid. So we need to look for exotic hardware. And this, sorry, there's a lot of, you don't have to read all this. There's some pretty pictures. This is stolen from a review article that Science editors did several years ago. And they were painting a picture of the most compelling quantum computer hardwares that are out there. And these systems are all very exotic. They're either very low temperature, the ones in solid state like superconducting loops or silicon quantum dots, diamond vacancies. You have these single defects in diamond, neutral atoms. These all have to be either kept very cold in the case of solid state systems, but neutral atoms and trapped ions, these two have to be kept in a vacuum chamber. So there's something exotic, something that isolates the qubit, the quantum bit, the memory element itself from the environment. And I'm going to talk about the one I know best, which is arguably in the lead, and that is these trapped ions I showed you in my first slide. So once again, this picture of a bunch of ions, this chip that you see here, it is a semiconductor chip, but there's nothing quantum about it. There's about 100 electrodes on this little bow tie in the middle. And these atoms, there's exactly 80 of them that hover above the surface of this chip by about 1/10 of a millimeter. And they're held in a vacuum chamber. These electrodes have electrical potentials that produce electric force fields that hold the atom, they hold the atom in place. And of course, we send laser beams across the surface to poke the atoms, to measure them, to initialize them, but also to do these gates, these quantum gates that allow us to express an algorithm. Okay, so pretty exotic. You're not used to a computer being composed of individual atoms, all identical atoms, floating in space. Well, that is the leading architecture right now for quantum computers. So I want to give you a little animation on how this works, and it's going to turn out to be a lot of optics. Okay, the idea is, here's the chip over here. And this is just an optical switch. It generates lots of beams, in this case, only 32, but if I can get this thing started. So we have 32 beams, and they're all focused to hit an individual atom. And these beams, we can turn them on and off to run switches. So the first thing we do is we initialize all the atoms in a certain state with a different laser beam. And then we execute a gate. So time goes from left to right here. And the wiring, the effective wiring of these qubits is through laser beams. You can see when the laser beam hits an atom, the atom is actually, it's actually moving. And that allows us to change the charge interaction and execute a gate, basically. So we're going from atomic physics to very high level computer science here, expressing a gate. And then finally we make a measurement, and the measurement is very clean in this case. We send a laser beam across the atoms, and oops, let me go back to that. And if the atoms are in if the atoms are in a particular state, 0, then they don't glow. If they're in the state 1, then they do glow. So we can just read off 0s and 1s on these individual atoms. And you saw the picture of these atoms. We can clearly resolve them on a camera. By the way, a sense of scale, these atoms are about 5 millionths of a meter apart. That sounds small, but atoms are 1,000 times smaller than that. This is they're miles apart, atomically speaking. And we can clearly resolve them like you would with good optics, looking up at the sky, resolving a couple of stars. Now, the one hard part with this type of apparatus is that it requires a lot of controls. In fact, this is a monstrous optical table. It's 4 feet wide by 16 feet across. The atoms are held in this tiny section. You can barely see it here, a vacuum chamber. Everything else, all these wires, is a lot of optics. Those are our controls, our eyes and ears on the atoms. And I guess I show this picture because you should sort of think of unwieldy computer, I guess. So, harking back to the days of vacuum tube computers. However, help is on the way because this is a physics laboratory. Now, when we build a quantum computer, we don't necessarily want to be doing physics at this level. We want to not have everything float so flexible. We need a healthy dose of engineering here. So without much exaggeration, we've crammed all of the stuff you see here into this box in the last couple of years, except the students. No, we didn't fit the students in there. The good news is that the students don't even have to be in this laboratory. So inside this meter cubed box is what's called an ion trap, these individual atoms. And there's a bunch of optics that control them. And we have, we run this obviously via a regular computer, and we can run that from home. We can run it elsewhere. And we can execute algorithms. And so building this apparatus and the one before it was sort of a turning point for me in my career, because I've spent over 20 years of my life making lasers more reliable, playing with atoms, understanding very fundamental interactions between atoms of light. Here we have a bunch of atoms and light, but it's all packaged up, and we're running quantum computing algorithms on a laptop in some other office. I'm not doing atomic physics anymore. We're doing quantum computer science. In fact, the system is so stable that we don't open this box we can run this box closed for many months at a time. And so we're starting to do other types of physics or computer science or mathematics or chemistry that, well, frankly, I wasn't trained in any of this stuff. And that's what makes the field so fun, because I'm always a student. That makes any field fun if you have to always be a student. Well, I guess that either means you're not so smart. Can't claim I mean, I know a lot about very little things here, but it's just fun learning things like magnetism. I won't get into too much depth here, but in this experiment, we had exactly 53 atoms in a line, and we observed a new type of a phase transition in magnetism. We made it so that each of these atoms, they have an effective interaction, or a cost function if you want. And we make them interact so that they want to form large domains where they're all in the same state next to each other. And as we vary a background effective magnetic field, we see a minimum in the characteristic size of these domains. It's called the dynamic phase transition. It's actually a subject in non-equilibrium condensed matter physics. But we were able to do something that we couldn't calculate using a classical computer. Why? Because 53 qubits, that's a lot. 2 to the power of 53, that's like 10 to the power of 15. That's a million billion configurations. And we can't, our classical computer is not powerful enough to deal with that and find out where this phase transition occurs. Another one more recently has hit our lab, has to do with wormholes and teleporting through a wormhole, believe it or not. It turns out that there's a model of something called a wormhole that can exist between black holes that has to do with quantum entanglement, the spooky action at distance. And with a small quantum computer, believe it or not, we can run certain tests of how information could traverse a wormhole and how its entropy changes and so forth. This is wonderful. People like Lenny Susskind and John Preskill, Juan Maldacena and Patrick Hayden. I love spending time with their students and their group to learn, what they can learn from our quantum computer in this very, frontier area of physics. And as I mentioned, this machine was kept under wraps. And in fact, it just started to work well about a year ago in January. And when we had the COVID shutdown starting in March, actually this experiment started taking data that was better than ever, partly because the building was a ghost town. There were no vibrations, the air conditioning was pristine. And so these are Marco Cetina and Crystal Knoll sort of lead the group. We've been running algorithm after algorithm from home, all with this box closed, and obviously here, everybody at home. So that's been kind of fun. And that's but one group in my academic group at the University of Maryland, soon to be at Duke. But you might guess that there's sort of an industry view of building this device. And down the street from the University of Maryland, my partner, Jungsang Kim here on the left, and I formed a company called IonQ. It's a quantum computing startup. Right now, we're at about 70 employees. It's venture capital funded. And we started raising money about 4 years ago, and we've built several generations of ion trap quantum computers that are really pushing the state of the art in the ability to express the algorithms. We want more qubits and more gates. And I'll cut to the chase. They're not yet big enough to challenge the biggest computers on arbitrary problems, but we know how to get there, and we are getting there. This is an example of sort of the level of automation that the IonQ team has. So this is a close-up of that chip I showed, the little bow tie. Here we're loading one atom in there at a time. This takes about a minute. We wanted to load exactly 24, and they come from this loading zone, and they get shuttled like a roller coaster down to the interaction zone. They're in a zigzag configuration. We stretch them out with the electrodes. We refocus the optics. Boom, ready to go. So here we have 24 qubits, and we can run algorithms on them. Now, how would you scale this up, and why are we only dealing with 10 or 20 qubits right now? Well, 53 is pretty big. We really need to get to many hundreds, many thousands even. And so we have to have a recipe for scale. And this is really what the company IonQ is up to. Now, one way here to think about scaling, the problem is we can't just add more and more to a single crystal, because that requires many more laser beams, and that scaling problem is a little bit difficult. But if we think about the Turing machine, remember we had the tape and the head, we can think of a head of laser beams hitting some centralized number of atoms here, and we can shuttle the atoms around, sort of like the tape, moving back and forth. And so that's one way to scale. And the shuttling idea, my colleague Dave Wineland, back in 2000, we started thinking about how to do this. It clearly requires lots of engineering on building a chip trap that's capable of shuttling atoms around and so forth. We sort of already know how to do that, as you've seen in the loading animation I gave you. So that's one way. But a very much more promising way in the long run is to take a page from silicon. If you've heard of a multi-core quantum processor, it has a bunch of individual chips that are sort of wired together. We can think about doing that with these trapped ions by having individual modules in red, and we can actually move the qubit with fiber optics, single photons that can interfere and create entanglement. And this is a modular way to scale, which I think is going to be really important for any industrial approach. Having a modular quantum computer, we can sort of plug and play multiple modules. And eventually we'll use very cutting edge photonics that are integrated on chip, perhaps on the chip that even traps the atoms. Now, another activity at IonQ has been to put our systems on commercial cloud servers. Again, they're still small, but we have a couple of systems that both Microsoft Azure and AWS have featured on their web servers. So I want to sort of step back, and I mean, I've told you a little bit about university approaches in this field, and at least the technology I work with, but also industrial approaches. And there's a little bit of a disconnect, I would say, between what goes on at the university and what goes on in industry. In quantum computing, it's a wonderful activity for a university because we teach quantum physics, everybody's comfortable with it. The real problem though, at universities, we don't build things. We do research. We don't build things so that they can be reliable and people can use them without knowing what's inside. That's what industry does. The problem with industry is some of them aren't so familiar with quantum physics. Some of them don't believe it. I mean, would you believe it? After after spending 40 years in engineering, somebody telling you, oh, this only persists as long as you don't look at it. That sounds kind of crazy. Well, quantum physics is true, and that's sort of changing, but we do need industrial systems engineers to pay attention to this field. There's sort of something in the middle. I would say the National Laboratory might be a good place to do this. And so far, the national labs haven't really taken this on, but they're showing signs of going real strong. In the US, we have something called the National Quantum Initiative that was passed a couple of years ago. I had a big hand personally in this bill, partly because I'm stuck inside the Beltway and was called downtown all the time. But this NQI unleashed well over $1 billion for the agencies to start to unleash centers of excellence, mostly Department of Energy and National Science Foundation centers across the country. Now, I should mention, and I'm not just saying this because you're Canada, but the country of Canada got kind of a bit of a head start compared to the US and much of the world. There are centers of excellence not only at UT, but also in Waterloo and Calgary. There's a nice startup infrastructure in the city of Toronto. There are several quantum startups. So we're sort of playing catch up here, but the Department of Energy laboratories in particular have deep pockets, and we look forward to their playing in this field. Hopefully we'll be able to bridge this gap between university and industry to help create quantum computers for science that might not be of interest to industry just yet, but we're going to need national laboratory research efforts to bridge that gap. So my last slide here is a little bit of a joke. I stole it from the cover of Technology Review from a couple of years ago. I think it was about the blockchain, but this could equally be a conclusion of quantum computing. There's a lot of hype in this field. I hope you got it crystal clear that we really don't know what the killer app is for quantum computers. It may be that we have to build them first and see what they're useful for. There's a rich history of that in all of technology, including classical computers. So there is a lot of hope, and there is something to the hype. There's no way to do certain problems in information theory and in computing without quantum computers. There's just no way. There's not enough space in the universe to store all that information. So thank you for your attention. Sorry for the hiccups early on, and I'm happy to take any questions you have.